So, so last time, in the last 3 lectures, we have talked about the kind of the basics of uniform convergence. I guess just a very quick review. So I think we have proved that the excess risk, this is in lecture 2, is bounded by this. This is the difference between empirical and population.
Can I please share your screen to the Zoom?
Oh, right. Thanks. Yeah, sorry, I forgot. Yeah, thanks for reminding me. It's gonna be a problem. I forgot to do that. How to? Yeah. Wait, I didn't join the Zoom meeting. Yeah. Sorry. Okay, cool. I guess now probably it's working. Yeah, thanks for reminding me. So, and so we have shown this. Right, so this is what we show in one of the claim in the lecture 2. So basically, this is saying that you only have to bound the difference between the population and the empirical for all theta. Right. So the most important thing is the second term, because the first term we have shown that it's something bounded by 1 over square root n. So so the goal is to show the second term, and we have discussed how to do it for finite hypothesis class, and also how to do it for infinite hypothesis class to get with a relatively brute force discretization technique. And so, and in the next few lectures, I guess we are gonna, as I kind of like mentioned before, so we're gonna have some other techniques to deal with the second term, so that we can have more informative bound. And today we are gonna take a small, in some sense, a small digression, or in some sense, a small preparation for some of the tools that we're gonna use for the next lecture. So in the next lecture, what we're gonna do is that we're gonna bound the expectation of this. So this is the next lecture. And this is expectation over the randomness of the data, right? So this quantity itself is a random variable, right? So because it depends on the data, the training data you have, because L hat depends on the training data. And next time we're going to upper bound this by some quantity which is called Rademacher complexity. So today we're going to do something that is useful for, it's a useful preparation for doing this. I guess, okay, so I guess here is the plan. So next lecture we're going to do this, and then the lecture, we're also going to deal with the difference between this and this expectation. Right, so that's the plan for the next lecture. So, and today what we're going to do is we're going to have some tools that prepare us for proving quantities like this, and so that the next time we don't have to kind of have a small section dealing with the tool in the middle. So I'm trying to kind of prepare us with the right tool for the next lecture. So a more concrete overview is the following. So the goal for this lecture is the following. So suppose you have some random variable x1 up to xn. So they are independent and random variables. So we're going to show 2 types of inequalities. So the first type of inequality is to show that if you take the sum of these kind of random variables, they are concentrated around the expectation. This is basically Hofstadter inequality is one type of this inequality. We are going to extend Hofstadter inequality to something more general. And second thing is that we're going to show that for certain type of function f, if you look at a general function, not necessarily just the sum of this random variable. Of course, you have to have some restrictions on what the functions f will look like. But suppose you have the right restriction, then you can show that even you have a function of x1 up to xn, it's still concentrated around the expectation of this function. And this will be particularly useful for showing this inequality. Maybe let's call this I here. So because you can, in some sense, maybe just to say one, this corresponds to L hat theta is close to L theta because L hat theta is of the form like x1 up to plus x2 up to xn, right? L theta is the expectation of L hat. And the second type of inequality will be useful for proving what I said, this equality one. So because if you care about something like this, is roughly equals to expectation. This is L hat. So then you can view this entire thing as a function, viewed as a function of your data of your training data, of your IAD training data. So this is a function of x1 up to xn, where these are the training data. So basically these kind of inequalities are called concentration inequality. The key kind of like idea is that if you have a family of IAD random variables, then first of all, if you take the sum of them, they become like Gaussian and they become concentrate, kind of like Gaussian-like, and they concentrate around the mean of the sum. And the same thing also happens if you apply certain kind of functions on x1 up to xn. I will tell you what kind of functions will have these kind of properties. And this kind of inequalities, not only useful for what we're going to do next, but also generally pretty useful for machine learning, like for statistical learning theory, because in some sense, if you think about what happens in learning theory, in many cases, basically you are trying to deal with the difference between an empirical distribution and a population distribution, right? So these kind of things will show up in many different cases, and that's also one of the reasons why I kind of like isolate this part as a single lecture to talk about technique. If it's just some kind of like a tool that is only useful for one lecture, then we can just invoke that as a lemma. But here, I think it's more useful than that. So that's why I want to kind of also show you how to prove some of these things, and also what kind of the limit. I'm not going to prove all the inequalities I'm going to show today, but I'm going to talk about some of the advanced version of the inequalities so that you know that they exist, and then when you need to use them, you can kind of find the right tools. So that's the overview of the lecture. So I guess, so let's start with the simple version, right? When you have a sum of independent random variable. And we have discussed this before about in the context of Hoffman inequality. I'm going to have a, kind of like a more kind of comprehensive discussion about this. So let's consider you have a random variable z, which is equals to sum of x1 up to xn, right? Xi's are independent. And so a warm-up is that what if you don't ignore what the structure of z is, right? So obviously you know that z is the sum of independent random variable. What if you ignore the structure? So what if we ignore the structure? So you still have something that you can show. You can still have some inequality that can show that z is close to the expectation. So here is the inequality, which is called Chebyshev inequality. I think probably you heard of this, in some of the probability class. So the inequality is saying that if the probability that z deviate from the expectation of z by some amount t is less than this thing, the variance of z over t squared. So it's pretty intuitive, right? So if the variance of z is small, then you have less deviation from the expectation. And of course, if t is bigger, right? If you look at a bigger window, then there's a smaller probability outside the window, right? So in some sense, if you draw this, it's something like, suppose you have a distribution that looks like maybe this, and the mean is here, expectation of z, And what this is saying is that if you look at the standard deviation, z, right? So suppose you look at this standard deviation z, and suppose you take t to be something like standard deviation of z times 1 over square root delta. You plug into this inequality. What you get is that the probability that you will deviate by this t is less than, maybe let's just write explicitly, and deviation of z over square root delta is less than delta, right? So this is saying that if you multiply standard deviation z by some quantity, by something like here, so suppose this is standard deviation of z times 1 over square root delta, delta is less than 1, then the probability in this tail is less than delta, right? So this is in some sense the weakest form of concentration that you always have, like without using any structure about the random variable z. So, however, this is not very strong, as we will see, because if you think about what happens with Gaussian, right? So let me see whether I missed a constant here. Yeah, I think this is right. Yeah. So if you think about let's see. So if you think about a Gaussian distribution, suppose you know z is Gaussian. So Gaussian z, then what you know is that so suppose z is something like from like 0, 1, right? Or maybe it doesn't matter whether the mean is 0. Let's say suppose the mean is mu. Then what you know is that z minus expectation of z is less than standard deviation of z times square root log 1 over delta. I guess maybe let's say this is just a general Gaussian distribution where the standard deviation is sigma, and this, so with probability at least 1 minus delta, you have this. So basically, if you have a Gaussian distribution, then what you have is that for the same failure probability delta, here you have a stronger bond. It's log 1 over delta instead of 1 over delta squared. So in some sense, what's it? I guess I'm not showing this. I haven't proved this for you, but you can do the calculation. So in some sense, this is saying that the tail, the tail decays faster for Gaussian. So basically, for Gaussian, you only have to multiply a little bit. So suppose this is Gaussian, you only have to consider standard deviation z times log 1 over delta square root. Then you know that the rest of the part has probability less than delta. But if you don't know it's Gaussian, then you have to be a little bit more generous in terms of the interval that you draw. Okay, so in some sense, like the goal that we're going to have is that we're going to show that if your z is a sum of random variable, then it's more like Gaussian instead of like a general, the worst case z. Or you have a better bond like this instead of like the bond like this from the Chebyshev inequality. So and also if you see if you look at it more kind of carefully on the consequences of these two inequalities, right? So maybe let's call this number 3 and this number 4. So if you have number 3, then you can, if you take delta to be something like inverse poly n, then you know that with high probability, right? So at least 1 minus 1 over poly n, z minus expectation z is less than standard deviation of z times square root log n. So basically, you only lose a log factor if you want to make the probability very high, right? So if you want to make a high probability event, then you only have to multiply by square root log n to the standard deviation, and then the rest of the probability becomes very small. However, if you use 3, if you use the number, wait, this is number 4. Sorry for the confusion. So if you use number 4, if it's Gaussian-like, then you get this. But if it's if you use number 3, then if you take delta to be if using take delta to be inverse Pauli, then what happens is that with high probability, you have this statement with high probability z minus expectation z is less than std of z over square root delta, which is std of z times Pauli. So there's a big difference between the additional factor here, right? So if you compare these two factors, you have a big difference. So that's why we want the so-called kind of the faster tail. So also the smaller tail, like in the inequality 4 instead of inequality 3. And a slightly alternative view, which we're gonna kind of like, in some sense, switch between these two views. Many, like they are equivalent, but like we're gonna switch this, very often. So the alternative view is that you can say that z minus expectation z is less than. So for Gaussian, what you have is that if you look at this, if you view this quantity like this, then you have this is less than expectation minus 2t squared over variance of z times n. So now you can compare this inequality, maybe let's call it 5, just temporarily, versus the Chebyshev inequality 1. So if you look at 1, then this is the right-hand side is decay with t in a polynomial way, right? So it's 1 over t squared. And if you look at 5, it decays exponentially fast as t goes to infinity. So that's another way to see the differences, right? So the tail probability for Gaussian distribution is decaying very fast, exponentially fast. But if you use the Chebyshev inequality, you only get a polynomially fast decaying inequality. And that's another way to see the differences. Okay, so we're going to look for the faster tail, right? That's what our goal. So the goal, just to repeat, so z, this is like a Gaussian. That's basically our goal. But of course, how do you say, in what sense this is like Gaussian? That's there are multiple different versions. We're going to formalize that. What does it mean by it's more like a Gaussian tail? So to do this formally, let's start with some definitions. So actually, we're going to define what it means by Gaussian-like to start with. So let's say a random variable x with finite mean. This is a one-dimensional random variable, mu, which is equals to expectation x, is called sub-Gaussian with parameter sigma if the following is true. Let me write it down. It's not very intuitive when you first look at it. Right. So I'm not expecting that you can see what this is really mean, but this is a definition for something is close to Gaussian, right? So, and this is not very intuitive, but a corollary is the following. So, so a corollary is that x is sigma sub-Gaussian if the following happens. It implies the following happens. So x minus mu larger than t is less than 2 times exponential minus 2t squared over 2 sigma squared t squared over 2 sigma squared for every t variance 0. So the corollary is probably intuitive, right? So if x is sub-Gaussian if you have this exponentially decaying tail bound, right? So this right-hand side it decays very fast in k as t goes to infinity. It's actually not only exponential in t, it's exponential in t squared. So this is, in some sense, this is a much more intuitive definition of sub-Gaussian. But the formal definition above will be more useful for the mathematical cleanness. But you can basically think of these two as equivalent. Actually, they are somewhat equivalent. Maybe before talking about that, let's say if you recall that if x is Gaussian, it's really literally Gaussian with variance sigma square, then this inequality, maybe let's call it 6, then this means 6 is true. I didn't prove this, but this is something relatively standard. So if you have a Gaussian with variance sigma square, then you can, if you do some kind of like calculation, do some integral, which is not super trivial, you have to do some calculation, but believe me, 6 is true, right? So basically sigma sub-Gaussian is saying that you have the same property as a Gaussian random variable with variance sigma square. And also, because of this, sigma square in the sub-Gaussian definition is often called variance proxy. So in some sense, if you are sigma sub-Gaussian, then the sigma is kind of like, you can think of as sigma square, you can think of as some kind of like pseudo variance. It's not exactly the variance, but it's the kind of alternative version of the variance, which actually is probably more important than the variance itself. So so that's the rough intuition. And also regarding these two definitions of this corollary 6, maybe let's call this 7. So 6 and 7 are in some sense equivalent definition up to some small constant, up to some constant factor. So what does that mean is that if you use 6 as a definition, then it means that suppose you use 6 as the definition, or suppose you satisfy 6, then you know that x is O of sigma sub-Gaussian under the definition, under the formal definition. So in some sense, if you don't care about the constant factor in front of the variance proxy, then these two definitions are, you can like 7 implies 6 and 6 also implies 7 up to a small constant loss. So basically the way that I always think about this is that I always think about 6 as the intuitive way that I think about it. But when I really use when I really need to use some properties about sub-Gaussian, and when I really kind of like want to prove something, I typically use 7. And also, I didn't tell you why these two equations are somewhat related, right? It still sounds like mysterious why they are related. And here is the reason why they are related. I guess what I'm going to do is that I'm going to show here 6 implies 7. I'm not going to show 7. Sorry, my memory is a bit different from my memory in the notes. That's why I'm a little confused. I'm going to show 7 implies 6. But 6 implies 7, would requires a different proof. But if I show 7 implies 6, you probably would kind of like get a little intuition why they are related quantities. So, so the kind of the general intuition is the following, right? So if you look at the Chebyshev bound, right? So Chebyshev inequality. How do you prove Chebyshev inequality? So the way that you prove Chebyshev inequality is something like this. So that you say the probability that z is minus expectation z is larger than t. This is equals to probability that z minus expectation z square is larger than t square. And then you use the so-called Markov inequality. You say that this is less than the expectation of this random variable over t squared. So the last step is using this Markov inequality. Is it called Markov? Yes, I think it is. So which is saying that if you look at the probability of some random variable, maybe let's call it y, is larger than t. This is smaller than the expectation of y less than t, right? Because if you have so much mass larger than t, then your expectation has to be high. That's basically the intuition. So and you can see that the way to prove Chebyshev inequality is that you raise to the power of 2. You raise to the second power. So that means that naturally you can also consider higher power and apply Markov inequality again. You'll get some other type of inequality. So if you consider higher moments, then what happens is that you may get something like this, right? So if, for example, you can say, I'm going to look at the false power. So the false power, this is still equal to this, right? Because you just raised everything to the false power, is still the same event. So this is equal to this. And then you can use the Markov inequality to get expectation z minus expectation of z to the power 4 over t to the 4. So now you see that you have a better dependency on t, better or faster dependency, or faster decay, maybe faster decay in t, right? Which is something we are looking for, right? We are finally aiming for exponential decay in t, but now we get something better than t squared. We get t to the 4. So, but of course, trade-off is that on top, right? This quantity on the top might be bigger in some sense than the variance, right? This is the false power of the deviation in some sense. So in some sense, you're going to get a trade-off, an implicit trade-off, right? So you get a better dependency on t, but you get a worse dependency in the numerator. So and you can try to do this with higher powers, like you raise to the power 6, raise to the power 8, so on and so forth, right? So actually, there are especially if you look at the early works, in this concentration inequality, people do raise to higher power. It turns out that there is a relatively simple way to deal with all the powers. This is which is called moment generating function. So this will make it cleaner, so that you don't have to deal with each of the power and see which one has the best trade-off. So the so-called moment generating functions is exactly this thing that we defined in this definition. We used in this definition of defining sub-Gaussian nullity. So this is the expectation of exponential of the deviation of between x and its expectation. So why this is an interesting quantity? So the reason is that if you Taylor expand this, the Taylor expand was inside, right? This is exponential of something, right? So Taylor expansion would be that 1 plus lambda times x minus ex plus lambda square over 2 times x minus ex square plus so on and so forth, right? So, and if you write it more formally, so this is something like sum over k from 0 to n, and the coefficient of Taylor expansion is lambda to the power k over k factorial times expectation, and you switch the expectation with the sum, you get expectation of x minus ex to the power k. So you can see that this moment generating function is really a mixture of different moments, right? Like you have all the moments, and every moment have a different weight in front of them. In some sense, this is saying that what we are going to do is that you're going to change the lambda so that you change the relative weight in front of all the moments, so that you can choose, in some sense, the right trade-off between which moment you are going to use so sometimes if you choose the right lambda, you're going to choose the right focus on the right moment and get the right dependency. So that's the rough intuition. And formally, if you really do this, mathematically, it's even simpler than this. So what you can have is that if you look at probability of x minus ex other than t, then this is formally the way you do the trade-off is the following. So you look at this and you say, I'm going to raise, instead of raising to the power, I'm going to use exponential. So this is equivalent to the exponentiated version is larger than exponential of lambda t, right? And then now you use Markov inequality for this exponentiated version. So you get expectation e of lambda x minus ex over, this is Markov inequality, e to the lambda t, Markov. And now you use the definition of the sub-Gaussian entity. So you say that, I guess I need to review what's the definition, maybe you already don't remember it. So the definition of sub-Gaussian entity is that the moment generating function is bounded by exponential of lambda square. That's the important thing, right? So there's a lambda square in the exponent. It's exponential of some quadratic function of lambda. So, and let's apply that, you get e to the sigma square, lambda square over 2 in the numerator and divided by e to the lambda t. So this is e to the sigma square, lambda square over 2 minus lambda t. And now you can see that in the exponent, you have a quadratic. And this quadratic looks like, wait, am I doing the right thing? So this is, right. So this is a quadratic that looks like this, right? Right, something, maybe not, there's maybe some, this is a quadratic that looks like this, right? And you can choose lambda, whatever you want, right? That's a free parameter. So that's why you want to choose the minimum lambda and minimize this quadratic so that you get the best bound. So take the best lambda, which means that you want to find the lambda that minimize this quadratic. That's relatively easy. You can just take the smallest lambda is the global minimum. You just do the derivative and make the derivative to be 0. And at the best lambda, it turns out to be t over sigma square. And you plug that in, then this is equals to e to the minus t square over 2 sigma square. So basically we show this is equation 7, right? This is the second, this is the corollary. I think it's equation 6. Equation 6. So basically you start with the Gaussian. So here you use the definition. So basically you use the definition of the sub-Gaussianality and you get this tail bound for this random variable. And also you can get the other side, right? So here you only know that x is not too much bigger than ex plus t. You can also get the other side. Less than minus t. And how do you do that? The trivial thing would be that you just flip. You define x prime to be minus x. And then probability that x prime minus ex prime is larger than t is the same as probability x minus ex is smaller than minus t. Right, just by the simple definition. And then you apply what we have already got on x prime. And then that implies what you have, the other side of the bound for x. But this is not super important, right? It's just the two sides are basically the same for our purpose. Okay, so I think, so what I have done so far? So I have defined this sub-Gaussian random variable. And I've argued that the sub-Gaussian random variable is basically saying that you have two ways, right? So one way is that the sub-Gaussian random variable basically means that you have a very fast tail, like a fast decaying tail, or the moment, some kind of moment. You can think of e to the lambda x minus mu as the moment. Some kind of moment is bounded. All the moments are bounded by something in this form. So far I only talked about one random variable. Right. But the reason why I care about this is the following theorem, which is the main gist in some sense. So it's saying that if you have all the xi's, right, all the independent random variables are sub-Gaussian, and the sum of them is also sub-Gaussian. So you can compose, and that's the biggest benefit of this sub-Gaussianality. Are independent sub-Gaussian random variable with variance proxy sigma 1 square up to sigma n square, respectively. Then, if you look at the sum of them, is also sub-Gaussian with variance proxy sum of sigma I square from 1 to 1. So this is, and as a corollary, because Z is sub-Gaussian with this variance proxy, you know that Z might, you have the concentration for Z, which is of this exponential form. Right, so you know that you have this tail that decays exponentially fast. So this is very important because, very useful and very important because now if you have a sum of independent random variables, you want to know how fast the tail decays, you can look at whether each of them is sub-Gaussian. I'm going to prove this in a moment. The proof is actually just the 2 lines, which is actually very cool. But before proving this statement, let me try to give you some examples on what random variables are sub-Gaussian, right? So basically, the applicability of this theorem depends on whether you can show each of the xi is sub-Gaussian. If you can show each of the xi is sub-Gaussian with very good parameter sigma i's, then this theorem applies, and you get a pretty good bound for the sum of them, right? So what random variables are sub-Gaussian, right? Like a single random variable are sub-Gaussian. So there are some examples here. By the way, whether your random variable is sub-Gaussian sometimes depends on what sigma you choose, right? So if you choose bigger and bigger sigma, there is at least either more chance that they can be sub-Gaussian. Of course, it's not guaranteed that if you choose sigma to be really, really big, you can be sub-Gaussian. That's not always guaranteed. But at least intuitively, it's not a binary question. It's not saying like this one is sub-Gaussian, this one is not. Sometimes it depends on what parameters you choose. So at least it's not always a binary question. For example, for Rademacher complexity, so for Rademacher variable just means that random variable, that's it. So basically means x is uniform from +1 -1, right? So this one I claim is sub-Gaussian. The reason is, intuitive. The reason is that if you look at this random variable, if you look at the density, it's something like you have a spike at 1 and spike at -1, right? So basically, density decays very fast after you go outside +1 -1. It decays, extremely fast. It becomes 0. That's why it's sub-Gaussian. And technically, you can say that you can prove this larger than t is less than 2 exponential minus t squared over a big constant c0 for c0 to be O of 1, maybe let's say 2. This is because if t is less than 1, then right-hand side is less than 1, is bigger than 1. So that's always true, right? I think I choose this so that, yes, because the right-hand side is equals to exponential minus 1 over c0. And if you take c0 to be a big constant, maybe 2, then this is larger than 1. So you verify this for t is less than 1. And then if t is bigger than 1, then the LHS is just 0. So that's why it's always also true. So that's why Rademacher a random variable. So that means that Rademacher random variable is O of 1 sub-Gaussian. Or sub-Gaussian with variance O of 1, with variance proxy O of 1. So, and similarly, you can prove that, similarly, if x minus e of x is bounded by m, so basically suppose you have a random variable where e of x is here, and if you look at a window of size m plus m minus m, right? So suppose your density is literally 0 outside, and you have maybe some whatever density we want, and literally 0 outside. Then once you go beyond the window m, then the density decays, extremely fast, or the density just becomes 0. So that's why this is, of M sub Gaussian. It's not, you still need to, to formally prove it, you still need to kind of like construct. You still verify the definition, of course, right? But I guess it's kind of intuitive that it's sub Gaussian just because the tail vanishes completely after you have the window M. And there's a stronger claim, which also get the right constant. Here I only have O of M, but you can actually get a stronger K, which get the exact height constant. So this is saying that if A is less than X is less than B, almost surely, so your random variable is almost surely bounded between A and B, then you can prove this. E to the lambda x minus EX, this kind of like moment generating function, is always less than e to the lambda square times you want the quadratic in lambda square, quadratic in lambda in the exponent, and you care about the constant because the constant is the variance proxy, and you can prove that this constant be a minus square over 8. And this is saying that x is sub-Gaussian with variance proxy b minus a over 2. And this is actually a homework question. It's not that trivial to prove it, actually. If you want to get a right constant, if you just want to get some constant, I think if you want to get, instead of 8, you want to get 2, it's relatively easy. If you want to get 8, you need to do a little bit, slightly more about it. We'll have some hint in the homework as well to help you to prove it. All right. So these are about all. So this is all about bounded random variables. Basically, this is saying that if you have a bounded random variable, it's going to be sub-Gaussian. And also, this works for Gaussian random variables, of course, right? So a Gaussian random variable has to be sub-Gaussian, right? So as we motivate it, right? So if x is from mu sigma square, then I guess formally you can prove the following. You can show that e to the lambda x minus EX. You can compute this. Actually, this is equals to exactly e to the sigma square lambda square over 2. So that's why it's sub-Gaussian with variance proxy sigma square. Okay. I think these are the bounded random variables and Gaussian random variables are probably the most important examples of sub-Gaussian random variables. And just a small, in the homework, we're going to talk about something called sub-exponential random variables, which is a weaker version of sub-Gaussian random variable. So, and this is precisely to deal with the fact that some random variables are not sub-Gaussian, whatever variance proxy you choose. So just to give you a rough sense on what the homework is about. So so here, when you define a sub-Gaussian random variable, you can in this corollary view, right? So this alternative view, here you have t square. So you insist that the decay is exponential in t square. And that's a relatively strong requirement. And there are random variables that doesn't have this fast decay. So for example, I think one typical example would be if you take the Gaussian square, if you square the Gaussian, which becomes I'm blanking on the name, what's called like chi-square distribution, right? So that one doesn't have this fast decay of tail. It's not t squared, it's t. So for these random variables, you still want to prove something about concentration, and you can still do them almost the same as sub-Gaussian random variable with some minor technical kind of differences, and that's what the homework, one of the homework question in homework 1 is about. So, all right, okay, cool. So, any questions so far? Okay, so now let's prove this theorem about this additivity of sub-Gaussian random variable. So proof of theorem. So our goal is to show that the sum of xi is sub-Gaussian, right? This is the goal. Right, so we just use the definition. We start with the definition. The definition is that if you want it to prove it to be sub-Gaussian, you need to look at the moment generating function. Sorry. I have some typos here. Let me mark it. Okay, so you look at the moment generating function. And so here you can see the nice thing about this, which is that you can, because this is exponential, you can decompose very easily. So you can write this as exponential lambda x1 minus ex1. Right. And again, because it's independent, you can switch the expectation, you can factorize. Right? Each of the xi's are independent. So you can switch the expectation with the product to get expectation e of lambda x1 minus ex1 times expectation of e lambda x2 minus ex2 okay, so this is using independence. And then you just say, I know that each of this random variable is sub-Gaussian, so I just use my definition that each of the random variable is sigma I squared sub-Gaussian. So you bound it by e to the lambda 1 lambda squared sigma 1 squared over 2 times e to the lambda squared sigma 2 squared over 2. This is by definition. And then you get this is e to the lambda squared over 2 times sum of sigma I squared. And you get this. That means that sum of xi is sum of sigma I squared sub-Gaussian, right? So this is the variance proxy. For sum of xi's. And you can see that the kind of the benefit of using this moment generating function, right? The exponential is because you can factorize the exponential easily, right? So if you don't use exponential, if you, for example, use the fourth power or the 8th power, right? You wouldn't have such a nice simple proof. Any other questions? Okay, so so that's the first part of the lecture, right? Which is about a sum of independent random variables. And now I'm going to talk about a more complex function of independent random variables. So now I'm going to talk about something like this. How does this kind of things concentrate? And you can see that in some sense, you want to say that this function f, when f is kind of close to a summation, in some sense, right, in some weak sense, then you still have very similar type of bound. That's the spirit. And but what does it mean by close to summation? We'll see. So here is the theorem, one of the theorem, which is actually something we're going to use for our future lecture, which is called McDermott inequality. So there is a bunch of conditions. So suppose you have a function f, I guess little f is the capital F I wrote before. So you have a function f satisfy the so-called bounded difference condition. What does the bounded difference condition mean? So it's saying that for every choice of x1 up to xn and xi prime. So I guess for every I and every choice of x1 up to xn. By the way, here these xi's are little xi's because here I haven't got any random variables yet. These are just the generic like numbers. So for every I, for every choice of x1 up to xn, and for every xi prime, which will be used as a replacement for xi, if you look at these two quantities, one is that you apply f on x1 up to xn, and the other one is that you apply f on x1 up to xn, but replace xi by xi prime. So basically replace one coordinate by something else. And you look at what kind of changes you can make by doing this, and you assume that the maximum changes you can make is by Ci. So basically this is saying that you are not very sensitive to, this function is not sensitive to changing a single variable, a single coordinate, a single input, a single coordinate of the input. And if you have this bounded, so-called bounded difference condition, then you can say that let x1 up to xn, now they are capital X, be independent random variable, and we have probability that fx1 up to xn is deviate from its expectation by t is less than this exponential thing minus 2t squared over sum of ci squared I from 1 to n. So in other words, I guess, equivalently, you are basically saying that you are essentially saying that fx1 up to xn, this is sub-Gaussian with variance proxy, something like sum of ci squared, maybe a big O, right? If there is some constant that you may lose by doing a little bit. Like your variance proxy, like this is using the equivalence of the two definitions, right? So this is the more intuitive definition of sub-Gaussian, and if you change to the formal definition, you may lose a constant.
You suggested that we would remove this as functions f that kind of behave like sums.
Mm-hmm.
But would you say that this condition sort of looks like a sum? Like you could have if xi prime and xi differ by greater than ci.
Yeah. So yeah, that's a very good question. So I think before I forgot to repeat the question. So from now on I should try to repeat the question. The question was that I mentioned that you want to make some conditions on f which make it similar to the sum, right? So and why this is similar to the sum. Yeah. So first of all, I think a small clarification. I guess by similar is actually a very weak sense. You see that in some sense the all of these conditions becomes in some sense not very similar, but I think they're only similar in the sense that you want to make sure that no coordinate is very strongly influencing your final outcome. So when you have a sum, right? So if you change one coordinate, you wouldn't influence your final outcome much. And here is the same thing. So basically, I think whether it's a sum or not, it doesn't matter. It's really about whether you have certain kind of Lipschitzness property. So maybe just briefly, also we can verify that this condition contains the sum, at least, right? So that probably would be useful. So suppose you have fx1 up to xn is equals to sum of xi, and each of the xi is bounded by something like bi and other one by ai. And now suppose you change one of the xi, how much you can change the final outcome. So then you can say that you have the bounded difference condition where ci is equals to bi minus ai, because that's the biggest change you can make if you change one coordinate xi, right? So that's the maximum kind of like range of like changes for the sum. But you can see that you can imagine many other functions that have this property which doesn't look like sum at all, right? So indeed, more precisely, I think the kind of the intuition is that you want this function f to be somewhat Lipschitz, like in some sense, like Lipschitz or not super sensitive to individual things. Yeah, that's the general intuition.
Why don't we just impose that Lipschitz? I would need to condition the Lipschitz function.
Right. So the question was why don't just assume that f is Lipschitz, right? So this is a very good question, and the very short answer is that we don't know how to prove that version. Like we don't know how to prove that if f is Lipschitz, then it's you have this result. So a longer version is that people have been actually trying to kind of like, this is very like a lot of researchers, especially mathematicians, have worked on this area, and there's a question about what is the right definition of Lipschitzness. Like I guess you'll probably see in a moment. Like I'm going to show two more general versions, and they have slightly different definition of Lipschitzness, or like or the intuition of Lipschitzness. And they are somewhat complicated. It's not like as clean as you expect, just mostly because there are some technical challenges in those cases. And you will see also a case where if xi's are Gaussian, then you have a very clean theorem. You just literally, as you said, you just assume f is Lipschitz. We'll get to there in a moment.
So is there like a version that you can figure out? Basically, this here now you have this found, but if you know something about the tail of x, if you like change the boundedness to some sort of distance.
Right. So I guess your question is that here you need this absolute bound in some sense. So in some sense, to make sure you have this bounded difference condition, right? So you need some things that kind of to be absolutely bounded. For example, in the sum case where you need xi's to be absolutely bounded between a and bi, right? So and this is a little bit different from the intuition we had about sub-Gaussian, right? So before we were saying that if each random variable has a fast tail, then the sum also has a fast tail. But here you need some kind of absolute restrictions, right? So this is actually related to the answer I had before. Like if you look into all the technical details, actually it's not that easy to deal with a tail that can go to infinite. So there's some technical challenges here which prevent us to have something super clean, I would say. So for example, if you know xi's are Gaussian, we'll see that you have a very clean theorem. But if you don't know xi's are Gaussian, then it's kind of like technically very complicated to deal with the tail of each of the xi. And in some sense, you can imagine, right? So maybe this is a little bit too advanced, but like for example, if you have xi, right? So the tail is sub-Gaussian. Suppose xi is just Gaussian, right? So and if f can square it, right? So suppose in the function f you square xi inside somewhere, then xi becomes xi squared, and the tail becomes lower, as I said. So like when you square it, it becomes chi-square distribution. The tail becomes slower, and if you take the false power, it becomes even slower. So you have to somehow balance this, right? Like it's not only about the input; it's also about what f does, right? If f does something super bad to, for example, square your Gaussian or raise the Gaussian to the higher power, then the tail becomes slower and your concentration becomes worse. So that's the kind of the challenge. Okay, so yeah, so let me proceed with a more general version, and then I'm going to talk about the Gaussian version, and then at the end, suppose I have time, I'm going to prove this theorem. So this theorem is something we can prove ourselves without doing a lot of heavy work. But the theorem I'm going to introduce next is somewhat kind of like very challenging to prove. So this is a more general version. So I think this is theorem 3.18 in one of this book by, I guess if you look at the lecture notes, there is a formal, this is Van Handel. Yeah, so it's a book on probability theory. So in this book, they basically what happens is that they extend this bounded difference condition to something milder. And the definition is, so you start with some definition. This is d minus I. Let's define this to be fx1 up to xn minus, you take the inf over z, fx1 up to x minus 1, z. Right. So basically, you're saying that if you look at x and you change one of the coordinate, and you want to see how much you can make it smaller. Right. So because this quantity is always bigger than 0, so basically you're saying that how much you can make it smaller by changing one coordinate z. Right. Inf you can just think of inf as mean, so minimum. Right. So the difference between this and before is that before you require. So basically, before in McDermott, you require di minus fx to be less than ci for every x. Right here, you don't make that. You don't insist that. No, you have at least you have an x as an argument of this DIF. Right. So you define a sensitivity at every point. You didn't assume a global sensitivity thing. You talk about a sensitivity at x. Right, that's a quantity, and then you can also define the sensitivity on the other side, which is just sup and now these are two functions that measure the sensitivity at every point, but they are not global sensitivity. And now you can define a global sensitivity, d plus, which is the sup over all x minus. Now you take sup. But before taking sup, what's inside the sup is the sum of this. Square. So basically maybe let me first write down all the definitions and then interpret them. This is minus, not minus 1. So, and then maybe let me write a conclusion. So you get that probability fx1 up to xn minus expectation f other than t is less than expectation. It's exponential minus t squared over 4 d minus. So you have a little bit different bound for upper side and lower side, which is probably not important for many cases. But just for the sake of completeness, let's write both of them. For d plus. Right. So I guess x1 and fxn are independent, of course. Dependent. Okay. So this is the theorem. So I guess the important thing is that what is this d plus and d minus, and how does it different from McDermott, right? So basically, I think the difference is that when you do the CI in a McDermott is you take sup over x1 up to xn, and then di plus fx1 up to xn. You first take sup, right? This is a CI, right, which is a global sensitivity for the ith coordinate. And then the sum of CI squared, the variance proxy in the McDermott, is you take sum over I from 1 to n, then you take sup over x1 up to xn, di plus fx1 up to xn. Right, square. So basically, you look at the global sensitivity for every coordinate, and then you take the sum over n. And here, the difference is that this d plus or d minus, right? So you are first you are taking the sum of their sensitivity over all coordinates at this point x. Right? You first take the sum, and then you take the sup. So you know, it's not that easy to find a concrete example to see the differences of these two, but I guess you can imagine the order of doing the sup and the sum it does matter, right? So it's possible that, for example, you have a point x such that only for one coordinate you are very sensitive, and for other coordinates you are not very sensitive. So that then you take the sum and then you take the maximum. It's more advantage to do that, right? So and in some sense, I think the mathematicians spend a lot of time thinking about how do you change the order. So the best thing you want to do is you take the sup at the very, very end, right? So like this one. But this one actually there's a small sup somewhere in the middle, because in the definition of DIF you still have this inf, right? So the best thing would be that you just define the sensitivity for everything like a gradient, and then you take sup at the very, very end, which is what I'm going to show for Gaussian distribution. But this is the best we can know for general distribution, right? So you look at the sensitivity at every coordinate, and you take the sum of all the sensitivity, and then you take sup of x. But the sensitivity have to be defined in this sense. Does it make some sense? Yeah, I'm not expecting you to understand all the nuances. Like I don't even understand exactly all the nuances. Like I need to open a book to see. To find the cases where there's a difference. I think there are actually indeed quite some differences like between these two inequalities, but it's not like you probably wouldn't be able to trivially see the differences. Okay, so and now let's answer this question about what happens if all the xi's are unbounded, right? So what happens if x1 up to xn are unbounded? If these are unbounded, like Gaussian random variable, even if you take f to be a sum, you probably wouldn't satisfy the bounded difference condition. You wouldn't satisfy this condition here either in this improved case, because here there's an inf here, right? So even f is a sum and xi's are Gaussian, this one would be infinity, right? Because there's no bound for any individual variable. There's no absolute bound for any individual random variable. So that's the next question. How do we deal with the case when x1 up to xn are not bounded? And there are some existing results along this line. So the first result is called Poincaré inequality, which is one of the very beautiful results. Also for other reasons, not only for the reason for concentration inequality, but also like for other reasons not related to this course. So this is inequality saying the following. So if x1 up to xn are Gaussian, which means 0 and 1. So, and you have some function f, right? So, and you can look at the variance of this function. You didn't prove that this is sub-Gaussian. You only showed a bound on the variance, which is something necessary to have, right? So if you don't have a bound at the variance, you probably wouldn't be able to show it is sub-Gaussian. So the variance is less than, this is exactly as suggested before in the question. So this is less than the gradient square, and you take expectation over the random variable x, right? So this is an expectation of the gradient of this random variable. So this is in some sense the ideal type of right-hand side that you would hope for. So the concentration of this random variable f is somehow controlled by how sensitive, how Lipschitz the function f is. So this is the idealistic and the basically the best kind of like thing you can hope for. But the limitation here is that on the left-hand side you only control the variance, you didn't control the tail explicitly. Right. So if you want to turn the variance to a tail bound, you have to use the Chebyshev. You get 1/t² bound. Right. So, and you can also deal with this like with other kind of like a Gaussian random variable. It doesn't have to be like mean 0 and 1. That's easy. And the strongest thing here is the following. So here is the stronger theorem which we can deal with the tail. So here you suppose f is L Lipschitz, and with respect to Euclidean measure, Euclidean distance, which is saying that fx minus fy is less than L times x minus y squared for every x and y in power. So in some sense, this is saying that basically this is saying that the gradient of fx is uniformly bounded by L, right? So you can see that this is different from this one because here you require the gradient for every point to be less than L, and above you require the average gradient to be something small. So here we make a stronger assumption to say that this function is just the globally Lipschitz, and then you can have a stronger bound on the tail. So now let x1 up to xn be ID from Gaussian, and now you can have the tail bound that we would like to have. So this t is less than 2 exponential minus t squared over 2L squared. So basically fx is L sub Gaussian, maybe O of L sub Gaussian. But the L is not the expected gradient. The L is the absolute bound on the gradient. So you can kind of see the flavor of all of this concentration inequality. It really depends on, when you take the soup, when you take the expectation, like for different kind of conditions, you can have different theorems with different strength. Any questions?
The concrete inequality looks pretty interesting. Like this reminds me of like the concrete inequality in the PDE setting. There you would like if you have like higher smoothness of the path, then you would get like higher moments. So essentially get like higher moments. So variant and like fourth moments. Do you have a result with that?
I don't think I know on the exact result off the top of my head. I think the higher moment. Could you get a higher moment from the one below? I think if you want to have higher moment, you have to assume something stronger. That's my hunch. It's like, for example, this one below will give you a higher moment bound, right? So I'm not sure whether you can have a higher moment bound that has weaker conditions than this. I don't know. Also, I don't know too much about PDEs. So I could miss. I don't know everything. Like this is the only thing I know. Yeah, but indeed, this Poincare inequality has a lot of different applications, not only here. Okay, so we have. This is we have 15 minutes. Oh, we have 10 minutes. Yeah. So it's a little bit challenging for me to give the full proof for the McDermott inequality in 10 minutes, but I think I will try a little bit. Just if I couldn't have the full proof, I can give you a sketch, right? So that's the last thing I was planning to do, right? So like for all of the inequality above, like this Poincare inequality, this tail bound for Gaussian, I think they are beyond the scope of this course. Like we don't. We're already doing a lot of things like in the technical part. So these things probably, even I do it, I would just invoke a theorem from a book. So you don't need to know the proof. For the McDermott inequality, I don't think you need to know the proof, but I think the proof is kind of interesting to some extent. So it's probably worth showing. So let's try that in the next 10 minutes. So so we care about bounding. We care about something like this, right? And we have the bounded difference condition. And the high level kind of like intuition is that you want to. So this one can correlate. F of x1 up to xn is kind of like something. It could be a very complicated function of x1 up to xn, right? And somehow you still want to reduce it to a sum in some sense. But the reduction is not like straightforward. The reduction is like this. So the way you do it is the following. So you say that you define a sequence of random variables that define z0 to be the expectation of x1 up to xn. So this is just nothing. It's just a scalar, which is a constant. And then you define z1 to be expectation of fx1 up to xn, conditional x1. So what does this mean? This is a function. This is a function of x1. So basically, z1 is a function of x1, but you average out all the other xi's, right? So and you can also define zi, which is the expectation of x1 up to xn, conditional the first I random variable. So this is a function of x1 up to xi. So given x1 up to xi, this becomes a scalar because all the other randomness got averaged out. So in some sense, you can see that z0 doesn't have any randomness. And z1 has a little randomness because it's a function of random variable x1, so it's a random variable. And zi has more and more randomness. And zn is finally what you care about, which is the fully random case. And the important thing is that you care about zn minus z0, right? The f minus the expectation. And you can decompose this into a sequence of things, right? So like this telescoping sum. And this is what I mean by reduction to the sum. So basically now you have a sum of random variables, and you somehow kind of think of them as independent in some sense. They're definitely not exactly independent, but you're going to reuse the proof that you use for the summation. That's what we're going to see. So and if you look at this, right? So this is a function of x1, and this is a function of x2, of x1 and x2, so on and so forth. And this is a function of x1 up to x, and yeah, this depends on all the random variables. Okay, so and now let's try to see what we know about each of these zn, zi minus 1. Right. So first of all, we know that for every zi, if you take expectation of zi, this is expectation of fx1 up to xn. Right. So in the inside you have a function of x1 up to xi, and then outside you average out all the randomness of x1 up to xi again. So this is equals to this expectation of f, right? By this is called a total law of expectation, right? You take the expectation of the conditional thing, then you get the expectation. Okay. So this is equals to this, which is equals to basically z0. So and then this means that the expectation of zi minus zi minus 1 is equals to 0. So each of these random variable in this decomposition is mean 0. And let's say you have so basically the intuition is that if you define di to be zi minus 1, what you're going to do is that you're going to have in some sense you want to kind of like bound the moment generating function of each of the di, and then you say that because your final thing is a sum of the di, you can bound the moment generating function of the sum of the di. So let's work on each of the di first, right? So I guess I'm going to claim that zi minus zi minus 1 is always less than ci, where the ci is the boundary difference condition in the condition of the McDermott inequality. So how do I do that? I guess let me see whether I can simplify this proof a little bit. For the sake of time. Okay, I guess it doesn't. Okay, so let's only prove it for z1 minus z0, just in the interest of time. So if you look at z1 is expectation of x1 up to xn, condition x1. And if you so I guess you can replace the first one by the sup over all the possible choices of x1. Right. So, and after you do this, this quantity is not a function of x1 anymore. So it doesn't matter whether you condition x1 or not. So you literally just get expectation sup fz x2 up to xn. So let me see. And also you know that z1 is bigger than expectation if, for the same reason, xn. So in some sense, you have some kind of upper bound and lower bound for z1. I guess these two quantities are not exactly useful for the bound. What's really useful is this. So if you look at z1 minus z0, this is then, so this is expectation fx1 up to xn, condition x1 minus fx1 expectation fx1 up to xn. So so you can bound this by expectation sup using what we have done above. And minus expectation of fx1 xn. So here both the and then you can put this inside. It's like I think it's slightly confusing when you really look at the math, but intuitively what you are saying is that what the difference between z1 and z0 is only one coordinate, right? So but we know that if you change that one coordinate, you cannot make much difference. So right, so that's what we know, right? Like if for any x1, x2 up to xn, if you change only x1, you wouldn't make much of difference. That's why z1, z0 wouldn't make much of a difference, because the only thing different is x1. So, but okay, but maybe let me have the formal proof. Like so, on the other hand, you can also prove that the same thing. So you can prove this is larger than if z. So basically, I'm basically trying to say that the difference between z1 and z0 is upper and lower bounded by the extremal case, right, where you pick your z in the worst case. And this means that if you define this to be a1 and you define this to be a2, then maybe let's call this b1 and this a1. So you have an upper bound and a lower bound on z1 z minus z0, and you can show what's the upper bound and lower bound. So the b1 minus a1, right? So this will be expectation sup, this is the extremal case, minus the inf. right? So this is exactly the CIs that we define, right? So if you change your random variable in the, you change your input in the first coordinate, what you can change, right? So the maximum changes is C1. So this is less than C1 by condition. So basically, this is saying that Z1, Z0 is between B1 and A1, and B1 minus A1 is less than C1. So this is saying that each of the random variables Z1 minus Z0 is bounded in a small interval. And similarly, you can also show that Zi minus Zi minus 1 is bounded between something like Bi and Ai, and Bi minus Ai is also less than Ci. So recall that our final goal is Zi minus Z0, which is the sum of Zi minus Zi minus 1. And we have proved that each of these random variables is somewhat bounded in some small interval. And now we can use the moment generating function. So what you do is you take expectation of lambda Zn minus Z0. And this is expectation E of lambda sum of Zi minus Zi minus 1. So the first thing we have to do is to factorize them in some way, right? So how do we factorize them? We just use the conditional. We kind of like do the chain, in some sense, kind of the chain rule. So what you do is that you first condition down x1 up to xn minus 1. So then you have this expectation E lambda Zn minus Zn minus 1 conditional x1 up to xn minus 1. And when you condition on it, you get this, and then the rest of the things is a function of xn up to xn minus 1. Right. So this is a like what's inside your condition x1 up to xn minus 1, and this one only depends on right. So this is a function of x1 up to xn minus 1, and this is a function of xn. So that's why it's inside the expectation. And then this term, because Zn minus Zn minus 1 is bounded, and it's bounded in a strong sense, in the sense that for every possible choices for x, so like you know that this is a kind of absolute bound for Zn minus Zn minus 1, right? So we know that this lambda Zn minus 1, this is less than exponential of lambda square sigma Cn square over 2. This is because if you have a bounded random variable, and we know that it's sub-Gaussian, right? So you can verify this in various ways. One way to do it is you just actually this will show up in the homework. This is the one of the homework question we define, right? So like if you have a bounded random variable, it's sub-Gaussian, right? So and you can bound your moment generating function. So and then you can replace this term by this absolute quantity Cn squared over 2 and times the sum of the other terms. I think this is n minus 1. And then you peel off the second term again and again. So you do this iteratively. I guess given that we're already running out of time. So we get this. So if you have this, you can get something like this. I guess this is actually 8 if you really do it carefully. So yeah, I guess I would just sketch this. So this means that f minus expectation f, right? So is equals to sum of Zi minus Zi minus 1 is sub-Gaussian with variance proxy sigma squared. Okay, I guess that's the end of the proof. But this proof is optional. It's just that we have more time, so that's why I show the proof. Okay, any questions?
What from the step before the equation in the blue circle, the blue circle, is that just
here?
Yeah. There's definitely
okay.
Yeah, the end of that line, this one. Is that just based on like the variance?
You mean this one? Oh,
yeah, getting to that.
Yeah. So from here to here.
Yeah.
This is just a yeah. It's just a trivial step. Like, I guess maybe technically what I should write is maybe let me do this here. Just so if you want to do 2 steps, the first thing is you do this. Sorry, you just do this. You do the total expectation. You condition. You first condition x1 up to xn. We do this, right? So this is the law of total expectation. And then you found that this term is a constant when you condition x1 up to xn minus 1. So that's why you can move it outside. Yeah, there's nothing deep there. Yeah. Okay, sounds good. Okay, cool. So I guess see you next Monday. Thanks.